In this video, we're going to discuss a real-life application for determining the resonant frequency. This is an experimental analysis, and we're going to use a simple mass spring damper system design for our system, and we'll study a Cessna Nosewheel Shimmy. Disclaimer is that I am not a trained airplane mechanic, and this is not an airplane repair or problem diagnosis advice. This case study is only meant to show a real-life case for students to understand an example of resonant frequency effects. To determine resonant frequency, there is the phase plot that is often used, and I found this example on the Electronic Stack Exchange that provides a good explanation using a visual, and this explanation shows how to find the resonant frequency when it's difficult to visually identify it on the Bode plot. If it's difficult to identify on the Bode plot, then usually the phase plot is very helpful in figuring out the location of the resonant frequency. To determine the resonant frequency, this is their visual that they present. They have the amplitude on the y-axis and the frequency on the x-axis for the Bode plot. In these top rows, you can see that the resonant frequency is obvious. There is a peak, and that is where the frequency is, the resonant frequency. And then in this bottom left picture, they show the diagram of where the pole is, and then if you can imagine overlaying what the Bode plot looks like on it, you can see where the resonant frequency is. And then they have a top view of that, which we actually call the standard view. And you can see for a second order system where our two poles are. And there's the imaginary axis as the y-axis and the real axis as the x-axis. To determine the resonant frequency, we can see our phase plot on the left, and we note that our two poles will have a decrease of 90 degrees in phase per pole, so this gives us a total decrease of -1. So we have a -180 degree phase, which is a decrease when we have our two poles here at 1 Hertz frequency. And then in our gain plot on the right side with amplitude as our y-axis and frequency as our x-axis, we can visually see where the resonant frequency is. However, when we have values that are damped, we have a damped system where the value for damping is high, it's more difficult to see where that resonant peak is exactly. So you can see for Q equals 20, it's fairly easy to see where that resonant frequency is, but for Q equals 0.1, it's more difficult to see where that is. And similarly, going back to the phase diagram on the left side, if you see where Q equals 0.1, you can see that while the decrease is still 180 degrees, it's not as sharp of a slope compared to the Q equals 20, where there is a very sharp slope. However, that inflection point, regardless of the damping value, is still at -90 or half of those decreases from the poles. So now we're looking at the amplitude or the gain plot again, and this shows the various values. So as I mentioned earlier, we're looking at the peak for this resonant peak. There is the value for no damping, and then there's the critical damping. So this just gives you a visual and shows the equation for the peak curve as well. So bringing us into our real life application, I really like this example of a small airplane Nosewheel Shimmy. This is an airplane that weighs about 1,000 pounds or so. It's about the weight of a small car. With these airplanes, it's like a tricycle wheel. So you have two back wheels and you have one front wheel. When you land them, you touch down the back wheels first, and then after they're down on the runway, you'll then lower the nose and have the nose wheel touch down. So an interesting problem that can occur with these is that there is a displacement transmissibility problem, and you can actually tell where the resonant frequency occurs because there's that high gain. I'm just going to go back for a quick second to talking about this resonant frequency. So when you have this high gain at your resonant frequency, you will see that there is a higher displacement transmissibility. So can you think of other scenarios in your life where there are varied frequencies during operation of a machine? So maybe a fan, there's frequencies, the frequency that it rotates at. You could have your keys on a bungee keychain, and you can move them up and down. How does the machine operate around its resonant frequency or component resonant frequencies? What would that critical damping versus a underdamped system resonant peak look like? So in this example with the plane, while the pilot was landing the plane, the nose wheel dampener, which has a hydraulic fluid, was not working properly. The resonant frequency of the dampener with force on it was occurring when the wheel was being turned upon landing, when decelerating between 20 and 40 knots. The method used to stop the violent shaking of the aircraft was to remove pressure from the nose wheel while in the speed or frequency, when you make the conversion range, and then to touch the nose wheel down after getting below the resonant frequency range. The dampener will require adjustment by the maintenance team, and giving them this information allows them to diagnose the issue with the dampener and adjust it as necessary. As I stated, I'm not an airplane mechanic. I'm not sure how they fix this exactly, and what they determine is the actual cause of this issue. However, I thought that this was a very intriguing example of a situation where you have a violent shaking at the 20 to 40 knots range, but it does not shake outside of that. And that may also be due to the weight being put on the aircraft. So this is a video that you can watch to see the violent shaking. And the pilots are able to handle this scenario. This is actually, it looks very dramatic, and it can be for a student pilot, but it is not an uncontrollable situation by any means. This is relatively, if you're an experienced pilot, this is not a big deal, but it is something that needs to be fixed by the maintenance team. Thank you for watching. Please leave your questions, your research links, and further analysis critiques in the comments. I am a student in a lot of these aspects, just as you are, and I would love to have your knowledge added onto this. And a question I have for you is, have you experienced other interesting problems that you want to see an explanation for, that you would like me to dive into a little bit of the research for? What are some other phenomena that you would like to see an explanation for? So maybe you've seen something similar or something very different, and you are just very curious about how it works, why things happen, and I'll take a look at it and see if I can provide any helpful information. All right, thank you for watching. Bye.